So machines learn better with pizza, I hear, yeah?
Always. I'm just trying to wire forms up.
You just need to send them the picture emoji.
And then they're happy.
Yeah.
Need more pizza memes. All right, I'll start. Thanks everyone for coming to yet another lunch and learn session. So today we're talking about machine learning, obviously. And I think machine learning, also AI, artificial intelligence, being a buzzword for quite a while now. Like more and more people start talking about them, especially like companies like Apple and Google. They constantly mention, the power of machine learning and AI. So we thought, like, what exactly is machine learning? What exactly is AI? And how does it actually work? And how do they actually apply to us, especially in Explore? So this session, it's mostly non-technical. We'll just explore a few concepts, some of the basic concepts, as well as some of the, I guess, slightly more advanced topics that Lauren and I will take you through today. So machine learning and AI, it's been so popular to a degree that people start making jokes about them. So thanks to Chu and Adrian for sending me these jokes. I won't read them now, so just read them yourself. And this another one. And then finally, but jokes aside, what is AI? What is machine learning? So I think it was early this year, Sundar Pichai, who's the CEO of Google, he did an interview. And during the interview, he said, AI is one of the most important things that humanity is working on. It's more profound than electricity or fire. So that's his stance, and now you know why Google's spending so much money on AI and machine learning. And so, just Google, Apple, and a few other companies as well. So AI, what is AI? AI involves machines that can perform tasks that are characteristic of human intelligence. That's what AI is. It involves things like planning, understanding language, recognizing objects and sounds, learning, and problem solving. That's what AI is. And machine learning is simply a way of achieving AI. Some examples. The first one is actually from Google. Google last year, I believe, they released something to the public. Let's have a look. Hopefully this sounds.
Quick draw is a game a few of us at Google may play. You draw and your computer uses machine learning to guess what you draw. I see a square. What's the case? Oh, I know. It's true. It's an experiment that uses some of the same technology that helps you translate recognize handwriting. To understand handwriting or drawings, you don't just look at what the person drew. You look at how they actually drew it. Which strokes did they make first? Which direction did they draw them? You train the computer on millions of characters from hundreds of languages. And over time, it learns whether you wrote book or whether you wrote book. Training is a big part of how the computer can get your drawings correctly. As people, it's easy for us to look at these three drawings and know they're all cats, but to a computer they're very different. One is just a head, one has a full body, and one is just facial features. To get the computer to understand, you have to show it a lot of cat drawings. And then it starts to see patterns, like that almost all doodles of cats have pointy ears, a small nose, and whiskers. Of course, it doesn't always work. That's because it's only seen a few thousand doodles. But the more you play with it, the more it will learn, the better it will get the cats at.
Oh, I know. It's Kafka.
We put it on the web for anyone to play with. We hope it inspires other people to think about fun ways to use machine learning. You can play it at g.co/AI experiments.
How many of you have actually seen this? Only a few? Okay. So Google's got this, I guess, like AI experiment space where this is part of it, but they actually publish, I think, like 2 dozens of different ones. So I'll publish the slides after this, and then you can click on the link to find out more about what Google's been up to. Next one. This one is also about image recognition, and this is from Tesla. I'm not sure if you can see this, but there are legends here. So basically, it's trying to detect static objects, other vehicles, even like road signs and things like that. So then the car will decide what to do or how to drive, whether it needs to stop or not. So I'll just stop right here. So that's what Tesla's been doing. Tesla's obviously been partnering with a few different software vendors to actually make this work. I have one final example. This again is from Google. Some of you might have seen this. This is from, I think it was last month when Google did their annual developers conference, and this is what they showcased on stage. It's very impressive, so you need to listen carefully.
60% of small businesses don't have an online booking system set up. We think AI can help with this problem. So let's go back to this example. Let's say you want to ask Google to make you a haircut appointment on Tuesday between 10 and noon. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
How can I help you? Hi, I'm calling to book a haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service you would like, what service is she looking for? Just a look at haircut for now. Okay, we have it 10 o'clock. 10 a.m. is fine. Okay, what's your first name? The first name is Lisa? Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Great. Have a great day. Bye.
In case you couldn't tell, the one on the left is a machine. It's not a human. A lot of people, like if you weren't told this was a machine, you probably wouldn't notice. So in that case, it actually passed Turing test, which is the difference between a human and a machine. So that's actually really impressive. Although like the application right now is very limited, so it's only about like doing those kind of scenarios. Obviously it can't yet hold like a real conversation, but you can see where it's heading, right? Especially with that amount of sort of money involved to actually invest in AI from Google. Like, I can't wait to see what they will be releasing next year. So that's some of the real-world examples from big companies. So companies like Apple and Google, they both released a machine learning library. So as a developer, we can now actually use their libraries or SDKs to actually start implementing applications without knowing too much about how those machine learning algorithms work. So you can pretty much like require this library and then just start mucking around with it and start using the algorithms provided by those libraries to do all sorts of interesting things. Amazon's got some, I'm sure Microsoft do as well. So there are a bunch of companies that use machine learning to various degrees. NVIDIA is probably like the most underrated or under the radar kind of companies around because obviously the world's biggest GPU manufacturer, and because how the difference between how CPUs and GPUs work, machine learning oftentimes run much faster on GPUs because they have like parallelized computing units much more than CPUs can handle. So NVIDIA is a pretty big player in the field. They're also recruiting worldwide. They've been spamming people's inbox. Anyway, one day we'll get to that, which is Westworld. Last night's episode was epic. So if you don't watch it, I recommend you do. It's a very good TV series. So we've seen some examples, but the question is, how do we actually do machine learning? I think there are 3 disciplines, or 2, depending on how you actually count it: computer science, statistics, and mathematics. Mathematics is easy, right? Who thinks mathematics is actually easy? 2 people? For the rest of you, you know what you need to do? Study hard. You can make that. That's right. So there are various different approaches to machine learning. If we going to list them all, it's going to take days, if not weeks. This is just a tip of the iceberg. So today, instead of like, telling you all about what those algorithms are, what the differences are, Laura and I will each sort of deep dive into one topic to sort of explore them a bit more. Otherwise, yeah, anyway. So, without further ado, I'll hand over to Lauren.
Cool. So this is probably a good one to start with. So a lot of the examples you saw before at the beginning really involved a lot of image recognition and object detection. So kind of what the 2 main differences in these ones are is this is image recognition. So in here, you can see down the side here that we've got that the model has detected that there's a dog, a bicycle, and a car. It's giving these what we will equate to as percentages, but it doesn't tell you where in the picture they are. It's just that there's somewhere that they detected them. Object detection will give you something like this. So you can see that there's more than just the 3 that it's detected here. So you can see at the top it says a car, a truck, another artifact, a bicycle, dog, cat. So these won't always be exactly what it is. So it will give you all the things that it's detected, as well as the probability that it is something. And then it's your job to take the top one. So for instance, this one, it's probably less likely that it's a cat and more likely that it's a dog. Hence why in this one it says dog. That's kind of the main differences between them, as well as it will give you in object detection where in the image it has detected it. So this is really handy if you need to, like for instance, draw a box on it, or if you're doing some sort of augmented reality and you want to place something there or kind of interact with it a bit more. So how does this work? So before we kind of get into the real nitty-gritty of how it gets to here, I thought I'd give you a bit of a brief history in terms of how we got to where we are today with image recognition. So it really all starts with, well, in the most recent census, this thing called ImageNet. So ImageNet is a project that's purely online, and it's basically a large visual database of images. So it actually contains 14 million images. And this was created so specifically for the purpose of having software recognize images. So in 2010, ImageNet, they started a competition called the ImageNet Large Scale Visual Recognition Challenge. So in 2010, there was, anyone can enter this, and basically what you do is you come up with a model that can run through a subset of these images, so roughly about 1,000, and hopefully predict what is in them with about a pretty average error rate. So in 2010, that error rate was around about 25%. So 1 in 4 would be incorrect. In 2012, there was a submission for AlexNet from the Supervision Group. And this is really where it all kicks us off for the current era we're in with image recognition. So AlexNet was able to drop that 25% error rate down to 16%, which is a huge jump, considering that's only 2 years. So this is kind of, AlexNet has been really standard for image recognition for a while. And then, as you can, no surprises here, there was an entry in 2014 by Google called Inception. And this is the model that a lot of the current image recognition is based on. So this was a huge jump. So Inception V1 took that 16% down to 6.4%. So it predicts it pretty accurately. The current model we're at is Inception V3. So they've actually open sourced this, so anyone can download that model and use it. This one now sits at 3.6%. Good question. So a guy wanted to test that. His name was Andre. He achieved 5.1%. Yes. So obviously, like, this isn't 100% the computer's better, because humans were able to get the context of a picture rather than saying it's a dog. We can see it's a dog in a kennel, whereas this would say it's a dog and a kennel. So there's slight differences, so it's a bit misleading, but still it's getting pretty damn good. So talking about all these things called models and all this sort of stuff, it's been hard to kind of visualize what this looks like. So without scaring too many people, this is kind of what a machine learning model will look like. Something like this. So there's a little legend down here which you can kind of see, and I'll just roughly run you through it. So Inception is what we call a convolutional neural network. So that means that each kind of section will feed into another, so it sends its data on to something else. So it acts a lot like the brain does. So each neuron will be passing information to another one, and it will do the processing on that. So the similarities are here. You can see these sort of connections you have, and sometimes they go down to 1 and then they spread out again. So very similar to how the brain works. So these orangey, yellowy, I guess they're yellow, I don't know, peach. So these steps here are the convolution. So I'll explain all this in a little bit more detail, and there's a lot of tech words which I still get very confused about what exactly they are. That's kind of one of the biggest hurdles with machine learning, is the terminology that they'll use. So once you kind of understand what it does, it's easier to remember things. So with Inception, the first few ones are this convolution, and then it jumps into, getting more data, and then gradually flows right through to the end, which is here where you really get your result. So there's a ton of layers that are involved. So we will kind of start roughly at the beginning as what do you need to do and where that kind of sits. So probably everyone else gets, yeah, that's bloody confusing. I don't really know what that means. So what you need to do that before you're actually able to pass in this image of, say, a cat or whatever, and give it to this model, and for it to predict what a cat is, you need to train it. So a lot of people, like, the way you do that is specifically with images. You will train this model on kind of the subset of things you want. So the easiest way in the implementation you do that is to have a lot of folders, and you'll give those folders names. So you'd have a cat folder. Inside that folder, you would have roughly, preferably over 100 images of a cat. So that, and then roughly all different. So then you can get a vast range of hits for that. So you can have as many classes as you want. So the Inception model was trained on, as I said, with the ImageNet data. So that is 1,000 images, but that can be up to 20,000 categories. So over time, they have kind of got Inception a lot better, so it can detect up to 20,000 different objects. So once you've trained all your data, which is actually trained your model, it's the most intensive part in terms of time. So sometimes it can take a few minutes, sometimes it can take a few days to train your data, your model. So once you've actually got a model that's working, which is a whole other story, and that's a whole other side of things, it will output something that looks like this. So you'll have these indexes here and a percentage. So the indexes will map back to your labels or your folders of your images. So the first one will be 0, and sort of so on. And then from there, you do the mapping back. So 0 is a cat, dog, monkey. And from here, you can see that's most likely would be a cat. So once you've got your trained model working, and you've fed in sort of test images and you're getting the right response, you're now ready to use that. So now we'll go through what happens when you want to check that that's a cat. So how this all works when you put it together in terms of using it. So the first thing you need to do is make sure that the data you're going to put into your model is what it's expecting. So Inception itself takes an image of 299 pixels wide by 299 pixels high. So if we've got this image here, which is like 590 by 428, we need to resize it first. So that's the first thing you need to do, is we've made it the correct size. And down here, we'll just see. So batch is 1 because we're having one image. Width and height. And channels is 3 because we've split up into the color channels. So you've got red, green, blue. So once we've resized it, the next thing we need to do is split it up into those channels. So then you'll have something like that. So you've got all your red data, or your green data, and all your blue data. So once we split it up, we need to put into something the computer or the machine is actually going to understand, and that is in float, or basically numbers. So this will become something like this. Definitely not to scale. So this would actually be 299 rows by 299 rows of 3 each. These numbers are obviously not matching, so just ignore them. So whenever, in the next sort of few slides, whenever I have the picture, we don't actually feed in the picture, we feed in this data. So that's the first thing you do before you can even use any of these Inception models or whatever you're doing. So the first steps of that diagram of the model we saw is the convolution layer. So the point of these layers, we actually spoke about it before in the video for the GoPro. Yeah, what the thing was called. So these layers are responsible for sort of identifying things of interest in the picture. And the way you do that is you will get your image. So remember, this will be allowed data of all those numbers. And what we want to do is we want to progress over that image and kind of get something that's of interest in that. So for this one, we're setting a window of 3, which means we want to get 3 pixels in this instance. And a stride of 1 means that every time you move, it moves across 1 pixel. So it is important to have some overlapping, just because it's easier to kind of identify things that way. So just for this demonstration, we'll just look at the cat ear. So just say we were looking at this bit, our input would be this little ear here. So for us, it's really easy to tell that that's an ear. But what exactly makes up an ear? It could be that there's a curve up here that then goes back down again. It could be that there's some straight lines in there indicating that there's some fur. So each convolution layer or each little node you saw in that diagram will do something different. It could be curves, edges, straight lines. It could be looking for the color orange. And if you remember that diagram before, there was a whole lot of those layers. Pretty much us as sort of lay people won't know what a lot of those do. It just works like magic. But the idea is that you feed in this little section. So this will be the same size as your window here, so 3. You can set it to whatever you need to, 3, 5, whatever. And then you feed that into this network here, and it will output another array of things. So this might be that it's detected that there's a curve here. So a lot of this other stuff will be, say, zeros, and where you've got the curve, you might have some numbers here. So just because we've got numbers, it indicates that there's something happening of interest right there. So all these filters will be looking for different, I guess, areas of importance. So if you're looking for the color red, that particular number for red, you might be looking more towards the 255 value, which is like all red. So it'll detect if that's red. So once you've got your output of these, you do that for every single one of those little boxes until you've done the whole image. Once you've got that output, it's going to look something like that for that whole picture. And in this, for each of those layers, there's going to be a whole lot of stuff that we just don't care about, so it's not important. So one of the other steps, which is on that diagram as well, it's got a pooling layer. Now there's different types of pooling layers. You can have ones that you want to get like the most interesting bit, so something that's really of high value. Or you might kind of be looking at the average, one that's kind of in the middle. So the most commonly used one is what's called a max pooling layer, which means that from that output we had of that convolution before, we only want to care about the really interesting stuff. So what you do is the same sort of tile or window that we saw before. You'd move along and say, for every like 4 of these, I want to get the most interesting. And so you'd find these little highlighted bits here, and you'd only grab those, and that will become your max pooled output. From this, you could feed that into another layer of convolution, or you could feed it into a fully connected layer. So this is really where the kind of guts of everything happens. So specifically for image recognition, this would be the layer that detects, you know, what a paw is or what a wheel is and what objects might have those things. So for instance, for us, for a cat, it's easy to, when we see an image of a cat, we know it's a cat because there's whiskers, tail, paws, fur, sort of little nose. But the way that the model has recognized that a cat has all these features is when we're doing our training set, it has decided that for itself, which is the really cool part. So this is where the fully connected layer comes into play. So once, there's probably a few of these layers, and I think there's 2 or 3 in the Inception model. But the last layer that's actually going to give us the data that we can use or we understand what it does is this softmax. So what that layer does is it's responsible for taking all these huge numbers that we get from all those layers which don't make sense to us and normalizing them. So putting them on a scale from 0 to 100. This is how we'll get our percentages. So down here you can see this data has been normalized. To begin with, this may have been like 15,000 and the point or the 0.02 may have been like 200 or something. So let's normalize them into this range. And then from that, for all of those numbers of categories that we had, you'll eventually get to this one here. So that's kind of a really high level of how Inception in particular works and image recognition. Object detection would take it a step further and have more of those sort of connected layers and convolutions to tell you where that interesting stuff is in that picture. Cool, so now back to Fred.
All right. So Lauren showed you image recognition, which is, obviously involves a lot of images. what I'm about to talk about is more about text. So there is this algorithm called naive Bayes, and it's more useful for text, although it can be used for images as well. So I'll talk about that. So what is naive Bayes? In machine learning, naive Bayes classifies a family of simple probabilistic classifiers based on applying Bayes theorem with strong naive independence assumptions between the features. Notice this Bayes theorem. What is that? Bayes theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. So that's what Bayes theorem is. Now, are you ready for some maths? This is what the formula looks like. Raise of hands if you understand this. Or Lex, would you like to explain? All right. Me neither. We can, though, translate that formula into more of a plain English. So posterior equals prior times likelihood divided by evidence. So that's the very, very basic formula of how naive Bayes works. There are a lot of different concepts to actually make naive Bayes classification work. First of them is called bag of words. Now, what that means is the bag of words model is a simplifying representation used in natural language processing and information retrieval. In this model, a text, such as a sentence or a document, is presented as a bag of its words, disregarding grammar and even the order, but keeping the multiplicity. That's from Wikipedia, what bag of words means. Now, in the more visual sense, let's say you've got this sentence as the input. You basically chop it up, right? Chop it up into separate words, put them in a bag. And the way you put them in a bag is that you calculate the number of occurrences of each word. So nice, 1, very, it doesn't have it yet, so 0, they, 1, and then you go through the whole sentence to actually keep adding them to the bag. That's what bag of words is. And it's important because based on that, you have the information of what are the words that are actually available in that document or in that sentence. And then you can do the calculations on that. So before I dive further deep down into some of the other concepts that are related, I will just show you a quick demo. And the demo, in order to do the demo, I need to use a library. And I'm using the world's best naive Bayes library. It's the best, just trust me on that. All right, let's have a look.
Has your name on it?
Well, maybe.
You want to be a fool.
So this is an Elixir library, by the way. So for all your Elixir devs out there, you can actually use this in your own system. Cool. I've got something prepared, so I don't have to actually type them all out. All right. So to show you how this works, first of all, I'll just paste this and execute it. These are the training data. So this is a training set, basically. And this is obviously an extremely simple version of it. Lauren mentioned that, for images, typically you need at least 100 for each category. So this is like, we've got like 3 sentences for each category. So apple, banana, and orange. This is extremely simplified. So in the real world, you will, provide it with, documents of data, megabytes of data or gigabytes of data in order for the training set to be useful. So this is the training. So I've assigned the training data to a variable, B. And now that we've got the training data, we can actually ask the machine to tell us this is the target. So this is the new sentence that the machine hasn't seen yet. It's seen some of these the data in the training set. It hasn't seen this yet, but I'm using a function to call this sentence with in order for the library to actually work out what this sentence is describing. So if I execute this, it says apple based on the training data set. Now, it tells you what it is. It could be wrong, right? In this case, it's right because I tweaked the training data, but it could be wrong. So this library also provides another function, another API, which is simply called classify. And what that gives you is the probabilities. So very similar to what Lauren showed you before, like you've got a probability of, in this case, apple is the most probable result for that sentence, but it could also be orange. There's a slight chance it could be banana, right? So that gives you, I guess, if we were to have like more than 3 categories, it'll actually show them all to you, like what the associated probabilities are for each category. So that's a quick demo of what this library does. And remember, it's the best naive-based library out there. All right. So naive-based has some real-world use cases as well. So let's look at some of those. It can be used for spam detection, sentiment analysis, topic categorization, and face recognition. That's the image part that the naive-based classification can work with. Naive-based is one, I guess, algorithm, but actually, within naive-based classification, there are multiple sub-models, probability models. The mathematical equation I showed you before is the high-level concept, but the actual probability models will have slightly different formulas. So let's look at them. There are actually 4 main ones: multinomial, binarized, multimodal, Bernoulli, and Gaussian. So the first 3 are typically used for text classification, and the final one, Gaussian, is more for image recognition. There are some differences between those 3, but what I showed you before is using the first algorithm. The other 2 are more like, in a simplified way of explaining this, is that the bag of words, for those 2 algorithms, they don't count the frequencies of the words appearing. So they only count, why it's called binarized is because it's 0 or 1. So a word either exists or it doesn't exist. That's what those 2 algorithms are. So I'm going to focus on the text classification. So there are a few more techniques that we use to make this whole thing work. First one is stop words. What are stop words? In computing, stop words are words which are filtered out before or after processing of natural language data. So, if you read a news article or you just read a paragraph of text, there are a lot of words that don't really influence the content or the context. So these words have very little meaning, so it doesn't influence the outcome of machine learning. Therefore, we don't actually need to process them. So in the world's best naive-based library, this is the default set of stop words. You can customize this, but these are the default. So these words typically don't mean much in the context of machine learning. So we filter them out. The second concept, it's called Laplace smoothing. What is that? What's smoothing? In statistics, additive smoothing, also called Laplace or Liston smoothing, is a technique used to smooth categorical data. But what does that mean? To smooth a data set is to create an approximating function that attempts to capture important patterns in the data while leaving out noise or other fine scale structures or rapid phenomena. This is what the definition is from Wikipedia. But it's still a bit hard to understand. So I actually searched around and found a Quora answer, which is more kind of understandable. Laplace smoothing is really about accepting the fact that your training data doesn't represent the whole world. Without Laplace smoothing, if a word was never seen in the training data, then the probability of that sentence is 0. Clearly, this is undesirable, so we apply Laplace smoothing to help deal with that. And if you notice that the small demo I showed you before, like there are only a few words that are in the training set. If we don't apply Laplace smoothing, then if we supply a sentence with a word that the training set does not contain, the probability will come out as 0. That's why it's undesirable. That's why we need to smooth it so that the probability can still be calculated correctly. So that's what that is. Now, another concept, TF-IDF, it's called term frequency inverse document frequency. And you might ask, what? In information retrieval, TF-IDF is a numerical statistic that is intended to reflect how important a word is to a document in a collection of corpus. It is often used as a weighting factor in searches of information retrieval, text mining, and user modeling. The TF-IDF value increases proportionally to the number of times a word appears in the document and is offset by the frequency of the word in the corpus. So that's the definition of it. And it's so popular that 83% of the recommendation engines actually use some form of TF-IDF. So imagine on Amazon, if you search for book recommendations based on your browsing history, purchase history, it'll have some form of TF-IDF in it. There's also this concept called stemming. Has anyone heard of this term? You have. For those of you still wondering what that is, in linguistic morphology and information retrieval, stemming is the process of reducing inflected or sometimes derived words to their word stem, base, or root form. I'll show you an example. So these words, they're all variants of, I guess, a word. So the word stem, in this case, will stem every single variance into the word explore. But that's not always the case. Like the final outcome doesn't actually necessarily have to be a real English word. It can be just, anything. But the important bit is that it stems those different words into a common form. And this is so that the machine learning algorithm can tell that, hey, if any of these words appear in the document, they're probably more likely to describe the same thing. So that's what stemming is. And by the way, it's the world's best stemming library available in Elixir as well. So please check it out and start it. Finally, there's one more concept, law of large numbers. Some of you might have heard of this. This concept doesn't necessarily apply just to text classification. It applies to any sort of machine learning algorithm. What that is, law of large numbers is a theorem that describes the result of performing the same experiment a large number of times. Why do we need that? Because according to the law, the average of the results obtained from a large number of trials should be close to the expected value and will tend to become closer as more trials are performed. And that's why companies like Google, they release those AI experiments for public users like us to actually experiment, because we're not only the users, we're actually the training, like the trainers. We're training Google's machine learning algorithms with the doodles and the whatever. whenever we use them, we actually we're contributing to the experiment. We're adding to the statistics. And finally, I'll hand back to Lauren to talk about how do we actually apply machine learning at Explore.
Yeah, so it's all well and good for us to describe all this stuff and kind of what it does, but not a whole lot of use if we don't know how to apply it or how we can use it. So I had a bit of a brainstorm, and this is definitely not an exhaustive list by any means, but so for our customers, this could look like being able to predict when a child's nappy will be changed or need to be changed based on the data we've collected prior. So for instance, like a certain age group might need their nappy changed more often than another age group, as well as other lots of factors there. So we can apply a classification to this one, and we may get a useful result. We may be able to reduce meal costs and wastage for centres based on what meals the kids are eating, how often they're eating it, all that sort of data. We could easily get the estimated sign in and sign out of a child based on their prior data, as well as, for instance, how far away the parents live. And if it's a Thursday, they might come in a bit later. This is more sort of specialized. We could even do things like income forecasting without even knowing too much about it, but we could do a lot of stuff with programming and planning, especially with, say, if a child is doing some sort of learning, we can sort of see that potentially that they might be having some learning difficulties. So if they're not picking up as quickly as other children based in their same age group or all those sort of other stuff. Potentially could minimize the spreading of the illness throughout a centre by possibly early detection of if a child is getting sick. This might be either not eating enough or their nappies that need to be changed more often. Or if they're, other children in the centre are getting sick and they're showing some sort of symptoms. You can even apply it to potential late fee payments that might be happening. So this is obviously just a whole very, very light list, but you can see where we're sort of going with this. So there's a lot of ways that we can help what we're doing existingly in terms of something that might be really, really useful to our customers. And for us internally, we may be able to help funnel customer support team specialists based on potential issues they're having. We could identify potential issues affecting multiple services by the frequency that they're happening or what features they're using. We can help improve our NPS. Those two kind of tie up a little bit. We may be able to identify services that are more likely to sign up to Explore based on geographical locations, their current providers that they're using, and all that different sort of data like that. So there's whole lots of applications here, but we don't really know what they are yet. So if anyone thinks of anything that they can see this happening to, so kind of a lot plus now. Thanks, that's all we've got today.
Thanks, everyone. Any questions? No? All good? All right. Thanks. Yeah.